In this video, we will start with Chapter 4 on linear models and matrix algebra. Section 4.1 is all about matrices and vectors and their introduction. But first, why do we need matrix algebra? It helps us expand linear models by more than one or two variables. As you saw in Chapter 3, it is still possible to solve a 2x2 matrix or a 2x2 system of equations using simple algebra. You can do the same using matrix algebra, but you can also expand this to, for example, a 3x3 system of equations or a 4x4 system of equations. The second helpful part of matrix algebra is that we can find a solution for a system of equation with the use of the determinant. A drawback is that it is only applicable to linear models. Therefore, it cannot be used in quadratic or cubed functions or exponents where we will use log functions. More on this later. So first, how do we expand our system of equations? So for example, we can have a product A11 from individual x1 plus his preference for product 2, which is A12 and x2, and this we can take all the way up to A1n, which would be individual 1's preferences for n number of products. We can do the same for a second individual. It then becomes A21 times x1 for the product x1's preference of individual 2. How much individual 2 would be willing to pay or preference for product 2, x2, would be A22 plus all the other products up to A2n xn, and this would be equal to D2. We can expand this downwards, m number of cases, and across up to a mn xn, and this would be equal to dn. So if you consider that you have 4 products, so m would be equal to 4 and 4 individuals. If you try to solve this equations using simple algebra, it will take a very long time because you would first have to set d1 equal to x1. You would have to replace x1 into d2's formula, then get a solution for x1 and work backwards multiple times to solve all your unknowns. With matrix algebra, it gives us a quicker solution. So a matrix is defined. A matrix is defined as a rectangular array of either numbers, parameters, or variables. With our system of equations, like we have above, so for example, 1 is a system of equation, we have 3 parts. First, a set of coefficients, which would be aij. Second, we have a set of variables, This is xi. And finally, we have a set of constants, which is di as well, or dj if you prefer a different subset to the x. So if we had to take this system of equations in 1 and rewrite it into these free coefficients in matrix forms, it will look like this. A is our set of coefficients. This would be A11, A12, up to A1n. Second row would be A21, A22, up to A2n. And we take this down in our matrix to AM1, AM2, AMN. In this case, our matrix is an M by N matrix, which means it has M rows and N columns. Okay. Second is our set of variables. In this case, we have x equal to x1, x2, all the way down to xn. And our set of coefficients, d, is equal to d1, d2, up to dn. dm. Write that properly. A note on our matrix notation. You can use the square brackets or round brackets, and in some cases we'll use only vertical lines. One more note, A11 is called an element of a matrix. So each of these entries in the matrix is an element. Okay. So let's do an example. If we have a system of equations x minus 3y plus 6z equal to minus 1. The second equation is 2x minus 5y plus 10z equal to 0. 3x minus 8y plus 17z equal to 1. To write this in matrix form, it would be our A matrix is equal to x, y, z. They're all lumped together. So x would be 1, y would be 3, and z would be 6. X in the second equation, which would be our second row, is 2, y is minus 5, minus 3 for y. There's two ways, I'll show you both, and 10. Final equation, final row, 3 minus 8 plus 17, and 17. So our coefficient matrix would look like this. As you can see, all the y's are negative. So you can have negative here or a negative y in your variable matrix. So our variable matrix X is equal to X, Y, our second unknown, and Z, our third unknown. And finally, our matrix of coefficients would be all these constants on the right hand side, so -1, 0, and 1. What is the dimensions of our matrix? It's a 3 by 3 matrix. This is 1, 2, 3 rows and 1 column, and this one is 1, 2, 3 rows and 1 column. The second part is vectors in this section. A vector is simply a special case of a matrix. And a vector is either one row or one column. So for example, x equal to x1, x2 up to xn, which is a 1 by n matrix, is a row vector, and y equal to y1, y1, y2 down to ym is a m by 1 matrix, which is a column vector. So in our example from above, our variable matrix as well as our constant matrix are by 1, so they are column vectors.